All right, hello everybody. We're looking at lesson 32, which will continue reaction types. For this one, I'm going to open the actual lesson. We'll have the slides for lesson 32. And then we're also going to want to look at, we're going to want to go to the support material, and you'll have this activity series that'll be shared with you the morning you're doing this. Just this little graphic right here. We want to look at this. So really, this lesson's pretty straightforward. If you understood, if you can recognize single and double replacement reactions, I think you'll be in good shape to do this lesson. So, first thing, we're going to add something to single replacement reactions. If you remember, a single replacement reaction is where one element replaces another element. So, activity is a term that will be described if an element is willing to lose or gain bonds. More active elements will force less active elements out of bonds. So if you look at this activity series we have, up top are the most active. These will always force any of the metals below them out of bonds. So if gold is bonded to something and lithium comes along, lithium's going to kick out gold and lithium will take over the bond. And then when the nonmetals are competing, we just have four halogens for now. If iodine is in a bond, then fluorine will kick out iodine. So whatever's on top will win. It's pretty much the whole point for activity series. So in the support section of Google Classroom, you can open this whenever you need it. And this will determine if a replacement reaction will or will not happen. So will gold react if it's placed in a sodium chloride solution? So in that way, you want to think about gold is looking to replace, because you'll always have a metal with a nonmetal when we're doing these. Sodium is the metal, chlorine is the nonmetal. So can gold replace sodium? Gold is Au, sodium is Na. If you need to open up your periodic table to look at that, you can do that as well. Will gold, Au, replace sodium, Na? Let's look. All right, so there's Na, sodium is right there, and where's gold, Au? Way down here. Can gold beat Na? No, it cannot. Na is higher up. So Na would replace gold, but gold cannot replace Na. So can that happen? No, the answer is no. Now let's decide, will chlorine react when placed in a magnesium bromide solution? So now we're talking about nonmetals. Chlorine is a nonmetal, and it's competing with the other nonmetal bromine. Will chlorine kick out bromine? Let's look at who wins between chlorine and bromine. Chlorine is right here. Bromine is just below it. Chlorine is higher. So when it comes to whether or not this will happen, chlorine is higher. So yes, that will happen. So with that, I want you guys to try to do, I think it's the first 5 questions. Try the first 5 questions. Use the activity series. Try the first 5 questions. So press pause. Do the first 5 questions. And then press play, and I'll go over it with you. Okay, first off, we have calcium competing with barium. Does calcium kick out barium? You see Ca is alone, now Ba is alone. What we're doing for these, we're deciding if they will happen. Can calcium beat barium? Here's calcium, barium is above it. So no, that will not happen, will not occur. Okay, Br, and now Cl is kicked out. Does Br kick out Cl? Does bromine beat chlorine? The answer is no. Next up, magnesium, and then you see nickel is alone. Does magnesium beat nickel? Mg is right here, and I is down here. Yes, magnesium beats nickel, so yes, it can happen. Okay, Mg is alone, Fe is alone. Does magnesium beat iron? Okay, we saw magnesium right here. Iron Fe is below it. Yes, magnesium beats iron. Number 5. Iron is alone. Now aluminum is alone. Does iron beat aluminum? Iron is right here. Aluminum is up here. No, it does not. So no, that will not happen. So that's all that we're doing for that. We're just looking at this and deciding which one will win. Okay, now we're going to go to something that happens in double replacement reactions. So in a double replacement reaction, remember what will happen is if you have A and Y is with, and then you have B and Z, A and B will swap places. So now A is with Z and B is with Y. You see that? they'll trade partners. The way it works, though, this is where you might have seen these down here occasionally. Normally, they don't matter that much. Now they're going to matter. AQ is an important distinction. AQ is telling you that this molecule is in what's called an aqueous state, which means it's going to dissolve when it's placed in water. S means it's solid. L would mean liquid, G would mean gas. So what happens right here in this double replacement reaction, you can see that PB is with NO3, but now PB is with the CrO4. K2 was with, or K was with the CrO4, but now the K is with the NO3. So you can see PB and K swap places. When they do that, though, when the lead, PB, and the chromate, CrO4, when they get together, they don't stay aqueous like everything else. They actually solidify and become a solid. It's an important detail. And normally in these reactions, the aqueous small elements, as soon as they're in water, they just disperse, but the solid stays as a chunk. So this would, like, you could form a crystal or something where if you have a pool of a liquid, a solid emerges out of it. That's what would happen here. The way we're going to do this, so first off, one detail, one product is solid, and we call the solid product a precipitate. Very important word right here. Precipitate is the solid product that will come out of this type of reaction. Everything else in this you can see is aqueous. See all these AQs on there. In the aqueous environment, ionization can occur. What ionization means is that the different ions, they break apart from the compound. So these will break apart into different ions. These will break into ions. The one thing, the precipitate doesn't break into ions. So look at this we have right here. Here's what it's going to look like when we break apart the ions. We're going to make what's called an ionic equation, where all the aqueous equations are broken into ions, but the insoluble compound, the solid, does not. So look, you start off with this. Look what you do with PbNO3. You split it up into just the lead and the NO3. They split up. Look at the K, the CrO4. Split up the K, the CrO4. Look right here, though. The PbCrO4, the lead chromate, that stays together. Why? Because it's not aqueous, it's a solid. And then the other aqueous part of this, the K and the NO3, they split up. So you have all these individual aqueous molecules, but the solid stays. So what's going to happen, look at what lead does. It starts off as aqueous. It becomes part of the precipitate. Also CrO4, aqueous becomes part of the precipitate. However, you'll notice that NO3 is just aqueous to begin with, aqueous at the end. K, aqueous to begin with, aqueous at the end. In this state, they don't do anything. Because they don't do anything, we call them spectator ions. And so you'll see the particles that did not participate in the reaction, that stay aqueous the whole time, are called spectator ions. And the last one, NO3 and K, are the spectator ions. And so you'll see that the final part of this will be what's called a net ionic equation, which is this down here. There's a lot on this slide, so it's probably easy to lose track of what's going on. This equation down here is called the net ionic equation. And so what you do, you take the ionic equation where you split up everything that's not a solid. And then right here, what you do, you eliminate the spectators. So the thing that's the solid right here, you just show the two reactants that lead to that solid. So we eliminate the NO3 from both sides, eliminate the K from both sides, and you just have lead and chromate make lead chromate. Because this is really all that matters if we're trying to make the solid. So what happens, PbCrO4 is the precipitate, and then the lead chromate is the precipitate, and then the potassium and the nitrate are the spectator ions. So right here, it's going to ask us, if we were doing this on paper, I would have you guys write out the entire ionic equation, break down all the ions, and then the net ionic equation where you eliminate spectators. But for this, since we're doing multiple choice, it'll be simpler. I'll just ask you to identify the spectators and the precipitate. So what's the precipitate? Well, obviously the precipitate right here is calcium carbonate, the solid that we get. And then what are the spectators? Well, that'll be the things that are aqueous on both sides, which would be the sodium, Na, and then the chlorine, Cl. So that's how we look at these, and we identify the precipitate, and we identify the spectators. So with that, I want you guys to go ahead, and I want you to try to finish the rest of this lesson. So finish this, then press pause. Do this. Press pause, you'll go over it, and then press play, and I'll go over it with you. Okay, so look at what we have right here. Here's the solid, AgCl. So what's the precipitate? That'll be AgCl. What is that? That's silver chloride. Silver chloride. Okay. What are the spectator ions? There's two of them. There's the H, the hydrogen, that's AQ on both sides, and the nitrate, that's AQ on both sides. So make sure you select hydrogen and nitrate. Number 8, CaCO3, that's the precipitate. It's solid. What's that called? Calcium carbonate. Calcium carbonate. Where are the spectators? That'll be the sodium and the chlorine. Sodium, chlorine. Last two. Where's the precipitate? Notice this time we're not making a solid, we're making liquid water. So what's the precipitate? That'll be the water. What are the spectators? That'll be the K, which is potassium, and the SO4, which is sulfate. And that's the end of it. So hopefully you don't find this too difficult. As always, email me if you have any questions.